The accident at 3 Mile Island, Unit 2, on March 28, 1979, captured the attention of the world. What happened in the accident and the actions taken to recover the plant are part of a cleanup story that is still not over. Basically, the accident occurred when water used to cool the nuclear core came out of the plant's reactor coolant system and spilled into the basement of the containment building. The core overheated and was severely damaged. The immediate problem facing the plant's owner, General Public Utilities Corporation, was regaining control and stabilizing the plant. Much of the instrumentation and auxiliary equipment used to monitor and protect the plant was damaged or inaccessible and not available for use. Access to key plant areas was severely restricted because of high radiation. The reactor building was completely inaccessible, as were significant portions of the auxiliary and fuel handling building. The situation was further aggravated by nearly 1 million gallons of highly contaminated water that had accumulated in the reactor building basement and in the auxiliary building. This was water that could not be cleaned up using existing TMI plant facilities. GPU faced a cleanup task unprecedented in the history of the American commercial nuclear industry. General Public Utilities immediately began assembling a recovery organization to address problem areas, drawing on expertise from its own company people, from contractors, and from experts on loan from many industry organizations. New systems for monitoring, controlling, and cooling the plant had to be designed from scratch. 3 separate decay heat removal systems were built, along with a system to control coolant inventory and pressure, and a new nuclear sampling system. A major decontamination campaign was begun in the plant's auxiliary building, and by the end of 1979, safe access was regained into that facility. The reactor building presented a much more difficult problem. In the years since the accident, it has been established that most of the radioactivity from the accident was contained within the reactor building. While that effective containment was good news, it also resulted in an interior environment that was extremely contaminated. Restoring necessary access to the reactor building would involve several major steps. A series of remotely controlled examinations provided engineers with samples of the atmosphere and the water that was in the basement. A video inspection through a penetration provided a limited view of the interior. It was determined that a significant accumulation of krypton-85 had built up in the building and would have to be vented. The venting of that krypton-85, some 43,000 curies, cleared the way for entering the reactor building. But the actual hands-on cleanup of containment was still a long way off. It became clear that the cleanup would be a careful step-by-step process, spread over a number of years, at a cost of $1 billion. Money to pay for the cleanup became a major obstacle. Funding was finally arranged in a carefully balanced plan that shared costs among several parties: the General Public Utilities Corporation and its customers, the states of Pennsylvania and New Jersey, the Japanese nuclear industry, the U.S. nuclear industry, and the United States Department of Energy. Beyond the cleanup, here was the first opportunity for scientists and engineers to learn about a heavily damaged commercial nuclear plant under real conditions. How did plant systems respond in the accident? How well was the radioactivity contained? What happened to the reactor core? And what were the safety and emergency planning implications for the industry and the general public? The U.S. Department of Energy assumed a lead role for the research and development work that would be needed, along with the acquisition and analysis of data from the accident, which would be significant in formulating future operating and safety standards. The gathering of information began when technicians made the first manned entries into the TMI-2 reactor building in the summer of 1980. One of the major projects facing engineers was the task of cleaning hundreds of thousands of gallons of radioactive accident water that spilled into the reactor building basement and into the plant's auxiliary building basement. This water was a potential hazard not only to cleanup workers but to the environment. It had to be cleaned and stored safely. GPU Nuclear, along with engineers from Bechtel, directed the design and construction of a one-of-a-kind processing system called the Submerged Demineralizer System, or SDS. It works much like a home water softener. Together with a smaller processing system known as Epicor, SDS removed virtually all of the radioactive material from the accident water. All of the solid waste generated in the cleanup of the accident water was shipped from TMI by the Department of Energy for research on the storage of high-level radioactive waste. The cleaned, processed water is being safely stored at 3 Mile Island. And that water has been reused in the decontamination work in the reactor building. With a technique called hydrolasing, contamination was washed from the floors, walls, pipes, and other large surface areas using high-pressure water sprays. Contamination was also removed from concrete using a process called scabbling. Air-operated chisels and hydraulic pounding machines break up the top layer of concrete. Some areas, like the reactor building basement, are not yet clean enough for technicians to safely enter. With money from the Electric Power Research Institute, the U.S. Department of Energy, and other organizations, specially designed remote-controlled machines have been sent into these areas. The machines do decontamination work and obtain data on physical and radiological conditions. Knowledge gained from work with these progressively more complex machines could have wide application in the future development of robotics. All of the decontamination work was in preparation for the biggest task of all, the removal of the damaged nuclear fuel from the TMI-2 reactor. Preliminary information on conditions in the reactor core was vital in preparing for this next big step. The first visual evidence of damage was obtained when a miniature underwater television camera was lowered through an opening in the top or head of the reactor. The operation was called Quick Look and was the first of several television inspections supported by DOE that established there was a void where the top 5 feet of the fuel core had collapsed into a bed of rubble. The next major step in the cleanup came with the removal of the massive 160-ton head from atop the reactor vessel. Removal of the head cleared the way for technicians to lower the miniature underwater television camera down along the inside wall of the reactor to the bottom of the vessel. The television camera confirmed the existence of another bed of rubble at the bottom of the reactor. Samples and videotape pictures enabled Department of Energy researchers to conclude for the first time that some of the nuclear core material had melted and flowed to the bottom of the reactor before cooling and solidifying. In May of 1985, the first direct access to the damaged fuel material was made possible with the removal of a 55-ton cylinder known as the upper plenum. In normal operation, this upper plenum holds in place the tops of the reactor's 177 fuel assemblies. Now, specially trained operators could begin working on the removal of the damaged nuclear fuel. A rotating work platform developed by Westinghouse in cooperation with the Department of Energy was installed on top of the open reactor vessel. By rotating this platform, all parts of the upper core debris bed can be reached. A 6-inch thick stainless steel floor shields the defueling operators from radiation. At 3 Mile Island Unit 2, defueling crews trained for months on a full-scale mock-up outside of the reactor building before starting this defueling work in October of 1985. Because of earlier decontamination and dose reduction work in the reactor building, defueling operators are exposed to levels of radiation comparable to what they would experience in defueling a normal operating nuclear plant. Using specially designed 35-foot long-handled tools, the technicians defuel the reactor working through a slot in the floor of the work platform. Suspended from the underside of the platform is a rotating carousel. It's designed to hold up to 5 12-foot long stainless steel fuel storage canisters. Technicians load core debris into these canisters. A specially designed underwater television camera system guides the defueling crew in their work. These videotape pictures came from this special television system. Some of the core debris is simply too large to fit into the 14-inch diameter canisters. Hydraulically operated cutting tools trim the material down to size. The United States Department of Energy will ultimately take custody of the entire TMI-2 damaged core. In the summer of 1986, the DOE began shipping the damaged core material by special rail car to the Idaho National Engineering Laboratory. The core will be the subject of ongoing research. Also in the summer of 1986, engineers got a first look at conditions below the rubble bed. A specially modified commercial drilling rig was mounted on top of the reactor vessel, and hollow core drill bits were used to bore into the damaged core. From each location, a drill string containing a cross-sectional sample of the core was extracted and placed into a defueling canister. Videotape surveys were then performed in each 3.5-inch diameter hole using miniature television cameras. Each box on this grid represents the location of a fuel bundle in the TMI-2 core. A total of 10 locations were drilled and surveyed. This allowed examination of a significant portion of the lower internals of the reactor vessel. These rods, which were below the waterline during the accident, appear bright and undamaged, except for some tearing caused by the drill. As the camera moves up, a transition zone between the intact rods and the rubble bed is visible. At this location, the undamaged portion of the fuel assembly is about 50 inches long. The upper part of the remaining core consists of a solid rock-like structure. Interspersed throughout this mass are metallic streaks and clumps. In the lower core region of location K9, we find a somewhat different scene. The transition zone from intact fuel rods to a solid mass occurs at only 10 inches from the bottom of the fuel assembly. Visible in this area is small debris between the fuel rods, all the way to the bottom of the fuel assembly. The material in this area near the center of the core is not as loose as that near the periphery. At this location, the solid mass is about 5 feet thick, thicker than all other drilled positions. Defueling the TMI-2 reactor is scheduled to take about 2 years. Some samples of the core material have already been sent to laboratories in Idaho, Illinois, Virginia, and the state of Washington. Laboratory analysis has already produced important new information on the nature of the accident and the manner in which the radioactive material was retained in the plant and not released to the environment. Lessons already learned from the TMI-2 experience have had a dramatic effect on the nuclear power industry around the world. But the prime lesson from the TMI-2 experience is that such an event must never happen again. Because of TMI-2, we are now better able to understand and deal with the long-term consequences of such an accident.